Howdy, I'm Tyler Clay.
I'm Mike Kirton.
I'm Madison Flussner.
I'm Kat Lewis.
I'm Max Murtaugh.
And I'm Aidan Wimhaw.
Today, we will present our senior capstone project.
Sandia National Laboratories tasked our team to design and construct a container to protect sensitive electronic contents from various hazards during transport. The idea is to create a container that can be used as a shield against temperature fluctuations like a freezer fire, electromagnetic interference like a lightning strike, and impact damage like a crash or a fall. A successful design will protect valuable, sensitive electronics even in drastic situations.
To validate the final product, Sandia gave us 3 tests. First, to protect the functionality of the electronic contents during a 16-foot drop test onto a hard surface. Second, insulate those contents from a 40-degree temperature change with a time constant greater than 250 seconds. Finally, dampen electromagnetic flux from an arc welder to 10% of its unprotected voltage.
The container needs to fit in a 20 by 20 by 20 inch space, weigh 22 pounds, and be assembled in 2 minutes or less.
In addition, the project requirements include creating an electronic sensing device, or sensor package, to test the container's protective capabilities. This sensor package measures acceleration, temperature, and electromagnetic flux to test the container design. The sensor package acts as the sensitive electronic contents that Sandia intends to put in this design and measures the extreme testing conditions.
The project requirements are similar to an airplane flight recorder, also known as a black box. While black boxes work in extreme impacts, they lack electromagnetic protection and the capability of exchanging contents. The team's project is a research prototype for a product that Sandia may further develop or implement in the future.
With the container parameters and test conditions defined, we set out to find a solution. How do we dissipate impact? How can we insulate? What shape should it be? No idea was dismissible.
Combining ideas to compose designs, the team created 4 prototype models. While each design had similar thermal and electrical insulation, the shape and impact damping differed. The cylinder shape showed promise for passing the tests, but impact uncertainty discarded the design. The pill shape had potential, but with only 16 feet to work with, the parachute would be difficult to deploy. A sphere proved too expensive and complicated to manufacture. The final model, a cube shape with a metal shell, foam layers, and a Faraday shield, would be simple, inexpensive, and effective.
While calculations proved the resilience of this design, its weight would exceed the project limitations, so we examined each component of the design to cut down on weight. Thermal analysis proved a dedicated thermal foam was unnecessary, and if taken out would allow for the box to be smaller.
Impact analysis and simulations showed that steel cutouts designed to buckle could make the box smaller, thinner, and lighter.
Material selection analysis allows us to minimize weight by choosing materials with ideal properties.
With a cubic shape, cutouts on the steel shell, polyurethane foam to insulate and dampen, and an aluminum Faraday shield protecting the sensor package, the design met all physical requirements.
We divided efforts to turn the design into a working model. Some performed calculations and analyzed risks to prove the validity of the finalized design. Some adjusted the 3D models to be sent off with materials for manufacturing. Others created the sensor package, which required a thermistor, accelerometer, and electromagnetic flux sensor.
The thermistor for temperature measurements and an accelerometer for acceleration measurements were ordered and tested by the team. An existing electromagnetic flux sensor meeting our requirements could not be found, so we had to design and build one ourselves. Our sensor was a 2-inch diameter coil of magnet wire with 250 turns to detect changes in voltage, like in a lightning strike, or in our case, an arc welder.
Once designed and properly tested, the sensors were ready to be integrated into the sensor package. We needed to connect not just the sensors, but a microcontroller, battery, SD card, LED display, and more. The solution was ordering a custom printed circuit board, or PCB. This allows for the simple and reliable connection of all sensor package components. With the sensor package designed, ordered, and assembled, we verified the sensors were recording data.
But there was a problem. The sampling rates in our code were too low for accurate data collection. After trial and error, we developed code that prioritized efficiency and speed. These changes allowed the systems to work at full potential, and the sensor package was finally ready to go into testing.
Another part of the team assembled and machined the steel, aluminum, and foam. The steel and aluminum sheets from the Fisher Engineering Design Center were cut to our design with a water jet. They were welded together to form the outer shell and the Faraday shield. The foam was cut to match the dimensions of the shell. At this point, our design had gone from paper to prototype and was finally ready for testing.
First, we found the weight of the box to be 15 pounds, meeting the weight requirements. Next, we measured the dimensions of the container to be 12 by 12 by 13 inches, which was within limitations. Finally, we assembled the box in under 2 minutes. All of the physical container demands had been met.
The temperature and arc tests were conducted without the protection of a container in order to establish a benchmark. The temperature test showed a time constant of only 30 seconds under the 250-second requirement, a promising result. The arc test read 5 volts, meaning the protected voltage should be less than 0.5 volts.
We need to perform a temperature and arc test before and after the box is dropped. The pre-drop arc test showed a better than required result, with the Faraday shield damping the arc 98% to just 0.1 volts. The pre-drop temperature test showed that even with 15 minutes in a 0-degree freezer, insulation and warmth from the active sensor package increased the temperature of the contents. The container successfully insulated the contents for both thermal and arc tests, but would the drop affect its capabilities?
Climbing 16 feet up a tower and securing the safety harness, we began countdown for the drop. Cameras rolling, the box hit the ground on its side, kicking up dirt and dust on impact. Analyzing the box revealed that only slight buckling had occurred on the steel shell, and while the outside remained intact, the inside was what really mattered. Inspection showed that nothing had been damaged on the sensor package, but analyzing the accelerometer told the story of what conditions it encountered. Sandia had set a target acceleration of 100 Gs, but the data read 225 Gs. Even though we missed the target, the circuit remained in working order. The container successfully passed the drop test.
To assess the impact damage on thermal insulation and the Faraday shield, the temperature and arc tests were repeated. Once again, the temperature increased during the test, meaning the insulation was still operational. The arc test yielded a maximum voltage of 0.1 volts, proving the Faraday shield survived the impact. We had achieved the project goal of making a container capable of protecting sensitive contents from impact damage, temperature flux, and electromagnetic forces.
But we didn't stop there. We wanted to test the limits of the container. So we upped the ante and performed a second drop test, 10 feet higher this time. Impacting the corner of the container, the outer damage was more severe with noticeable deformation on the edges, and when the team analyzed the data, we found the accelerometer read 500 Gs, 5 times the original desired acceleration. Despite this, the sensor package still worked and the container had survived an even greater impact force.
We were curious how the steel affected the impact, so we performed the 16-foot drop test again, this time without the protection of the external shell. When the container hit the ground, the outside layer had no visible damage and recorded acceleration peaks at 129 Gs. Initially surprised by this relatively low acceleration, we determined that the foam's compression increased time of impact, resulting in lower acceleration. Even our best efforts weren't enough to damage the sensor package protected by our container.
9 months ago, Sandia challenged us to develop a product that neither lightning, crash, heat, nor cold could damage. With diligent design, calculations, construction, and validation, that challenge has been met.
This project was a great learning experience for each of us, and we are so grateful.
I learned a new coding language.
I learned about welding.
I learned about risk evaluation and budgeting.
I learned 3D modeling.
I learned thermal and impact analysis.
I learned circuit design.
Thanks
Thanks
again,
again,
Jacob.
Jacob.